All right, at number 4 we have a swing hanging from a ceiling. And the length of that swing is 2 meters. And what we need to do is get potential energy at 3 different points. So the first point is when the swing's horizontal. B is when it's 30 degrees from vertical. And then C is when it's at bottom. Okay. And all the potential energies are going to be measured relative to the bottom, so we'll make that the reference level. And remember, the reference level is where H is 0. The potential energy will be 0. All right, so first let's look at when the swing's horizontal. When it's horizontal, it's like that. That's the swing. So the potential energy is mgh. So the child is 40, 9.8, and the height is what? How high above the reference level? 2. So that's 2. And with that we get 784 joules. We're going to jump down to C. When it's at the bottom, what's the height? 0, right? So if you did PE equals mgh, you got mg times 0, so there is no potential energy. Now, when it's 30 degrees, let's draw the swing at 30 degrees to vertical. So that's 30 degrees right there. Now, we're interested in, if we extend the reference level, we're interested in that height there. That's the height above the reference level. Now, to get that, well, we know that the swing is still 2 meters in length. And if we make a little right triangle here, and we get this height, let's call this x, then we can subtract from 2 and get that height. So the cosine of 30 is x over 2, making x 1.73. So this is 1.73, and then if you subtract 2 minus that, then this amount here is 0.27. So then PE equals mgh is 40 times 9.8 times 0.27, or 106 joules. So that's important. Now you know how to get the height, something like that.
This person will put his face on the line to demonstrate faith in the principle of energy conservation. A bowling ball pendulum is released from rest directly in front of the person's face. If energy is conserved, the ball cannot rise higher than its release point, and his face is safe. Should he be willing to bet on that? Let's find out. The ball is released and misses by a nose.
When does the ball, as it's swinging, so here's our pendulum, and it's swinging, when does it have the greatest kinetic energy? This one, right? This is KE is at a maximum. When is the kinetic energy at a minimum? Both sides, right? KE is a minimum because it stopped for an instant. However, potential is a maximum here, right? Because it has its most height above, if we make this the reference level. So the PE is a minimum there. So, and it's also a maximum over here. So we have this conversion happening from potential to kinetic to potential to kinetic to potential, and so on and so on and so on and so on. Okay, now, we already know that to change the kinetic energy of something, you need to do net work on it. So this is the equation that tells us that. Now, we said there are 3 forces on that ball, and forces are what can do work, right? So let's look at what work can be possibly done here. Gravity's doing work, so we could say the work done by gravity plus the work done by friction or air resistance plus any work done by tension. Those 3 works added together make up the net work. And they together will change the kinetic energy of the ball. Now, let's talk about tension for a second. The The tension force is because of the rope, right? And it's always directed in that direction, right? So it's actually centripetal. It's always directed towards the center. How does that tension force, the direction of the tension force, relate to the direction of the displacement at any given instant? 90 degrees, right? The displacement is always 90 degrees to the tension, which means that in terms of work, how much work does a force that's 90 degrees to the displacement do? Cosine 90 is 0, right? So tension is actually not doing any work. So that is not doing any work. So the tension force is not affecting the kinetic energy at all. Now, friction is doing work, right? That's why the ball is slowing down over time. Friction is what we would call a non-conservative force. Now there's that word conservation again. And we talked about conservation in the last chapter. A conserved quantity is what? Quantity that what? Stays the same, right? As the system evolves, that quantity stays the same. Momentum was like that. Energy is also a conserved quantity. So if we have a non-conservative force like friction, that means this is a factor that prevents the quantity we're studying from being conserved. So the reason that slows down is because the quantity we're studying, which is energy, is being removed from the system. It's not being conserved because of friction. Where is the energy going? Where's the energy going? What? No. Heat primarily, right? Thermal energy. So as that friction happens between the air and the ball, the air and the ball are getting a little bit warmer. So that energy of movement is being turned into thermal energy. So the energy is not conserved. Now what we're going to do is idealize, as we always do, and say that there is no friction. So if there is no friction, how much work does friction do? None. So the only thing doing work on that ball is gravity. Here's our equation for that. mg times hi minus hf. So all we have is gravity doing the work and changing the kinetic energy. So now let's tidy this up a little bit. So mg hi distribute to mg minus mg hf is the change in kinetic energy. And let's do this. Since we have an initial quantity here and one over here, we'll bring them to the same side. Okay, so we have all the initial quantities to the left and all the final quantities to the right. Does that equation look similar to another one? Maybe? Makes you think of one? Which one? The momentum one, right? So we're going to actually give this one a very similar name. This will be the law of conservation of energy. Now, I left a space here because there's a very important word we need to put there. Not kinetic, not potential, not thermal. We played hangman in the last class. We'll do it here too. Hold on, don't call out. You're going to get a head, a body, 2 legs, and 2 arms, and that's it.
No face.
No face. So, raise your hand if you have a letter. What? Jeff? No F. Alex?
E.
Josh? What? P.
Josh, remember in Mr. Black's class? Remember?
Oh my.
Wow, this guy's getting hung quick.
We played hangman the entire class at one time.
Oh yeah, I was good at that.
Come on. Now nobody wants to go. It's too risky. Great job.
How about A?
Ballsy.
I see
Should I
what
call
you're saying.
Trav or
That
not?
meta is a common
All
tool.
right, let's call Trevor first.
C.
Huh?
C.
Oh, I know what it is now.
Oh.
Wait.
Mechanical.
Raise your hand.
Put the C now.
Ryan?
Mechanical.
Yeah, see,
Put the
using
C
the wrong
now.
piece.
Oh, I did. Though.
Yeah,
That's embarrassing.
that doesn't make sense. But yes.
I wanted to hang him. All right. So now look, that word is what goes here. What does that word mechanical mean? Movement, right? So this type of law, this law is referring to a specific type of energy, mechanical energy, which is either kinetic or potential, because they all involve movement or either the potential to have movement. So that's why this law is called it. It's a very important adjective there, is mechanical. Because that's only good if we eliminate friction. If we don't eliminate friction, what happens to the mechanical energy? What kind does it become? Is with T. If we don't eliminate friction, our mechanical energy becomes thermal energy, right? So this is a very specific case of energy conservation. It's when there is no friction and the mechanical energy is conserved. So the motion will always stay the same because the energy is staying in the system. So that's what we'll do. We'll idealize and have no friction. So let me give you a slide with your definition of mechanical energy. So if mechanical energy was conserved with that pendulum and you held it up and touched your chin with it and you let go, what would happen? Come back up and touch your chin, right? If it didn't touch your chin and you just held it and let go, it would just go forever because there would no mechanical energy would be leaving and it would just swing forever. First is, let's figure out what is the speed of the rock when it is 1 meter above the ground. So what we want to know is the speed when it's here, right? When it fell there. So start with your conservation of mechanical energy. Now I'm going to do it two ways for part A because I want you to see. So in both cases it's starting here, so it's being dropped. So what is the VI? Zero, right? So that means the initial kinetic energy of the rock is zero. All right, so that's gone. So what we're left with is m times g times 3, because that's the initial height, equals 1/2 mvf squared plus mg times 1, right? Now if we want to solve for vf, you see that mass is going to cancel. But let's just leave it there for a second. So we would have 3 mg minus 1 mg, right? I'm bringing this over, is 1/2 mvf squared. So that's really 2 mg equals 1/2 mvf squared. Mass cancels. And so if you solve for vf, you have square root of, bring the 2 over, 2 times g, 2 times 2.0 times g. Now, remember that you can move your reference level wherever you want. And wherever your reference level is, that's where your height is 0, your potential energy is 0. So I'm going to put my reference level there. So if this is the reference level now for part A, h is 0 there. So let's look how this changes our equation, or how we have to do the work. Equation starts out the same. But the initial kinetic energy is still 0. If this is the reference level, what's the potential energy going to be at that point? 0, right? So this is now gone. So now you're just left with mghi. So the potential becomes the kinetic. And this simplifies to Vf, when masses cancel, is square root 2ghi, which is the same as this, right? Square root of 2 times 9.8. But now your height's only 2, because it's 0 to 2. The difference is 2. So it's the same thing. So make your reference level at a place that makes your equation a little more convenient. And when you do that, what you're going to find is that your equation's often just going to cancel out and come to that. So over time, you're just going to remember this, that if the object starts from rest, that your VF is just square root 2ghi. And it'll be like, it's kind of like a shortcut. Once you see it, you'll be able to keep using it. But that's only going to work if you put your reference level at the right place and your VI is 0.
Maybe just do mgh equals 1/2 m
And that even simplifies further to that. That's why that's what's so nice about this concept. It's just so, it's easy. It incorporates all that kinematic stuff we used to have to do. Part B,
So
go ahead, Ryan.
you'll never need to know the mass.
Not in this chapter. Later, as the year goes on, we're going to actually add to this equation, and the terms won't have mass in them.
But right now, like half BI squared, like you
Yeah.
can just take away the mass.
Yeah, it
That's all.
cancels out. Now B, it doesn't make sense to put the reference level here for part B because we're going all the way to the ground. So using this equation again, if we make the reference level at the bottom, both terms cancel out again. You're left with MGHI becomes kinetic. Mass cancels. VF is square root 2GHI. So it's 2 times 9.8, and now the height is what? The ground to the top?
3.
3. 7.7 meters per second. You see, this is actually the kinematics equation, right? That's what if you think about your kinematics, right, VI 0, so it's the same thing. Because we use that kinematics equation to build this concept. So that's why it ends up being there anyway.
This pendulum ball will be released from the height marked on the screen. When it reaches the bottom of its swing, a post will stop the top part of the string, but the ball will continue moving. How high will the ball rise on the other side of the swing? Lower, higher, or the same as the release height? The ball rises to the same height because the energy is conserved. Here's the demonstration repeated with a different initial height.
Here is an arrangement called an energy well. The V-shaped bottom of this track is a potential well in which a ball can roll back and forth. If the ball has insufficient energy to escape over the top, it is trapped in the well and can only oscillate back and forth. How much higher than the low side would it have to be released from in order to escape? A release point only slightly higher than the low side is sufficient for the ball to escape.
Raising a mass increases its gravitational potential energy. We'll use this triple track to show that this energy is conserved as it changes from one form to another. We'll release a rubber ball down each of these 3 tracks. Each track has a similar downhill section, but the uphill sides have different slopes. If a ball is released from the top of each track, how high will it rise on the other side in each case? Here's the ball rolling down the first track. The second track. The third track. The ball rises to the same height from which it was released in each case.